Welcome to this explainer. So, have you ever pulled out your phone, punched in a destination that's literally thousands of miles away, and just sort of marveled at how the perfect route pops up almost instantly? It honestly feels like magic. But the reality? Well, it's actually a super fascinating story of computational evolution. Today, we're going to dive into the seemingly impossible speed of modern routing apps, and we're going to do it by tracing the lineage of this massive mathematical hurdle all the way back to a 70-year-old algorithmic breakthrough.
Section 1. The impossible routing problem. To really appreciate what your phone is doing behind the scenes, we first have to zoom out and look at the sheer, terrifying scale of the obstacle we're up against.
Okay, let's put this into perspective. Say you want to drive from New York to San Francisco, and you want the absolute shortest path. In the North American road system alone, you're dealing with over 64 million individual intersections. If you do a simplified estimate, that leaves you with roughly 10 to the power of 220 possible routes. To wrap your head around that, even if a supercomputer could check 1 billion routes every single second, testing all of them one by one would still take over 10 to the power of 200 years. So basically, it is a mathematical impossibility to just brute force this problem. And that brings us to the core mystery we're exploring today. If testing every single route would literally take longer than the universe has even existed, how on earth does your phone bypass this mathematical impossibility and hand you the perfect route in like 4 seconds? Section 2, a 20-minute invention. To find the answer to that modern mystery, we actually have to zoom all the way back to a tiny cafe in Amsterdam in 1956. This was an era where the idea of an everyday computer was, frankly, considered laughable. The context behind this is just incredible. So, computer programmer Edgar Dijkstra was working on software for this early computer called Armac, and he desperately needed a relatable problem to prove to the public that computers were actually useful. I mean, at the time, they were considered such a joke that when Dijkstra tried to file his marriage license, the authorities literally rejected it. They said programmer wasn't a recognized job. He was forced to write down theoretical physicist instead. So, Dijkstra went looking for a demo that ordinary non-mathematicians could easily wrap their heads around. His highly relatable problem? Figuring out the shortest way to travel between 2 Dutch cities. Now, the initial go-to solution for routing back then was something called breadth-first search. You start at the source, explore all your immediate neighbors, branch out step by step, and stop when you hit your target. Simple, right? But there is a massive flaw. Breadth-first search treats all road lengths exactly the same. But in the real world, a winding country road and a straight highway just aren't the same distance. So this basic method totally fails to account for actual real-world driving. Dijkstra knew he needed a better method. And amazingly, sitting on a cafe terrace with his fiancée over a simple cup of coffee, he just figured it out. In just 20 minutes, without even using a pen or paper, he developed what we now call Dijkstra's algorithm. His big idea was to track the shortest distance, or the cost, from the source to each node. It methodically explored the lowest cost neighbor first, updating paths as it went along. Because it explored from lowest to highest cost, it mathematically guaranteed you'd find the absolute shortest path to any target. It was incredibly simple, perfectly elegant, and an absolute game changer. Section 3. The need for speed. Because while Dijkstra's algorithm gave us a mathematically flawless foundation, bringing it into our modern era reveals a massive bottleneck when you try to scale it up. Here's the issue. If you use basic Dijkstra's algorithm to map a trip from, say, Newark Airport to the Central Park Zoo, the search frontier sort of spills out equally in all directions. It ends up exploring over 65,000 intersections, completely wasting time searching illogical directions, like deep into Staten Island or large chunks of New Jersey. Now sure, it still solves that local query in about 1/10 of a second, but if you run it across the entire North American network for a long road trip, it averages out to 7 full seconds per path. With millions of users asking for directions all at once, a 7-second wait time would literally crash Google Maps servers. So, engineers tried to fix this spreading problem using a modified algorithm called A*. Think of it like this, where Dijkstra searches equally everywhere, A* mathematically stretches the map. It uses a heuristic to aggressively penalize moving in the opposite direction of your target. It basically says, hey, stop exploring backwards, and immediately heads toward the goal, which dramatically cuts down the number of intersections it has to check. But, as always, there's a major trade-off. While A* is brilliant at optimizing raw distance, which is exactly why video game characters use it to navigate mazes, it totally fails us on the open road.
When we're driving, we care about the fastest travel time, which means factoring in speed limits. And when forced to calculate time instead of raw distance, A*'s heuristic becomes an extreme underestimate. In fact, when optimizing for travel time, A** actually ends up exploring 3 times more nodes than a well-tuned Dijkstra algorithm. Okay, so engineers pivoted again. The next big iterative leap was bidirectional Dijkstra. Instead of just searching from point A to point B, the algorithm runs from both the source and the destination at the exact same time, until they meet in the middle. This essentially cuts the whole search area in half. Brilliant trick, right? But even with this, it was still fundamentally flawed. Why? Because it lacked basic human intuition. Section 4, ranking the roads. Think about how you intuitively drive. You naturally know to take winding local roads just long enough to hop onto a fast highway. And then you ride that highway until you absolutely need to hop back on local roads to reach your final spot. The problem is, algorithms don't intrinsically know the difference between an interstate highway and some twisty suburban cul-de-sac. To encode that kind of human street smarts into the code, engineers developed what are known as customizable contraction hierarchies. Rather than treating all roads as equal, the entire map is automatically pre-processed. The system hunts for massive bottlenecks that split the map, like, say, bridges crossing the Mississippi River, and it gives those critical intersections the highest rank. It systematically slices the map over and over, ranking the importance of every single node in the entire network. But there's a risk here, right? If the algorithm is only looking for major highways, what happens if a local road is actually the faster option? Well, to make sure it never misses a quicker local route, the system pre-calculates artificial shortcuts between lower-ranked local points. Now, these aren't new physical roads. They just represent the mathematical knowledge of a guaranteed fast local path. This ensures the algorithm can confidently ignore thousands of useless side streets while still perfectly guaranteeing it's giving you the absolute shortest route. And when you combine the whole shebang, this hierarchical pre-processing, those calculated shortcuts, and the bidirectional Dijkstra search, the results are absolutely breathtaking. A standard Dijkstra query that used to take 7 full seconds is instantly crushed down to an astonishing 200 microseconds. That is 35,000 times faster. To put that into perspective, here's exactly how that speed is achieved. Let's look at a massive trip from San Francisco all the way to Montreal. Instead of exploring all 64 million nodes across the continent, this modern algorithm clusters its search right around your start and endpoints. Once it hits the top of that road hierarchy we talked about, it only checks the most important cuts. So in the end, the search space shrinks by a factor of 44,000. It checks an incredibly tiny 1,236 nodes to route you across the entire continent. Just wow. Section 5, an enduring legacy. Because despite all these incredible modern layers of preprocessing and hierarchy, it is wild to realize that modern petabyte-scale routing still fundamentally relies on the exact same core logic that was mapped out in that Amsterdam cafe back in 1956. The enduring nature of Dijkstra's algorithm is absolutely no accident. He had this famous saying, "Simplicity is prerequisite for reliability." Remember, because he invented his solution completely in his head without pen and paper, he was literally forced to avoid all avoidable complexities. He kept his foundational solution so incredibly elegant that it allowed the math to be scaled infinitely, decades and decades after he conceived it.
Dijkstra deeply believed that the programmer, not the machine, was accountable for the elegance of the work. He really hoped his philosophy of careful, thoughtful simplicity would echo through generations of computer science. He literally said that if future programmers doing a quick and dirty fix just imagined him looking over their shoulder and chose elegance instead, well, that would be enough immortality for him. And that leaves us with a pretty profound thought to wrap up this explainer. We've just traced how a 20-minute invention, one that was just created to prove a room-sized computer wasn't a joke, now instantaneously navigates billions of human beings across the globe every single day. So looking at the simple, elegant ideas being quietly developed right now in our time, you really have to wonder, what foundational concepts are waiting in the wings today, just getting ready to map out the unimaginable complexities of our future? Thanks so much for exploring this with me today. And keep looking for that elegance hiding in plain sight.